so. There's no X on this one.
There should be, yes. Yes, you're
Oh,
allowed.
okay, good, okay,
Wait, I did set the
Yeah.
screen capture. Okay, yeah. Excellent.
good.
So same deal as yesterday.
Something on here.
Okay,
We're gonna see some discussion then.
yeah, 262. Yeah,
It's
the nice conference room.
Nice. See you later.
Yeah. No.
Hmm?
No, I thought my computer was frozen.
It's not there?
No, it's fine.
Okay. Whoops. Okay. Is that sound okay, or do you hear anything?
Yeah, I checked the microphone earlier. It had a very good response.
Ah, okay.
Should be fine.
Okay. Well, do we have anybody with us?
I think Celia's coming, and I think there's probably one other student that is coming around 9:30. I'm gonna see if there's anybody here online. Oh, we got one victim online. Excellent.
So we shall wait some 10, 15 minutes, or?
Yeah, maybe at least 5.
Uh,
Let's check to make sure that this is, Could you say something so I can hear the, oh wait, I can even hear myself speaking, so it should be fine. Okay.
yeah. Hello, hello.
Yep, we're good.
Okay, so everybody who's online, please stay with us. We'll wait for a few more clients, and then we'll get into it. If there's any questions, you're welcome to ask us question. You can probably, how's the communication with the online students?
So right now I've got the chat open in Zoom.
Ah, okay.
So, yeah, yesterday we just had a couple comments about the quality of the sound, which is why I was moving things around, but, yeah, so they're definitely present.
Present and hears. Okay.
Actually, it was interesting, last night I had an emergency meeting with one of my, someone I'm contracting with, who's trying to develop an alginate-based film. And she went and talked to some investors who were really frustrated that she didn't, after 6 months, have a product that was ready to market, because they want their return on investment. I'm just like, okay, look, if that's their attitude, these are the wrong people to be talking to, because these things take time,
Yeah, a PhD thesis is 5 years, no? And if
Yeah.
you want a solid, if you want something new, you invest at least one PhD, and that means about 3-4 masters and 3-4 bachelor theses, no?
Yep. Yeah, that was basically, what I told her, she's like, okay, all right.
That company I told you about, their Ongi, which they set up, no, to set the first product, they made 16 years. They made red numbers. After 16 years, they had 2 years where they were profitable. And then Bayer bought them, and due to the costs of Bayer, it was again deep red, no? The results for the next 2 years. Because, they increased the salary of all the people, no? Which Peter he said it's good that my employees get more money, no? And he said they paid him because they bought the company and he should have worked for 5 years as employed CEO, no? And he said he got twice as much as he paid himself all the time, no?
Wow.
And then he said the stuff like doing patents and all this kind of stuff, they had to pay to Bayer, I think about 150,000 euro, and that he did normally. Then bookkeeping was about 3 times as expensive, and I don't know whatsoever. No? And he said, I barely got that company into the black numbers, no? And with all those costs, of course, we were again deep red. It's incredible what those large companies, how they tear money away. No?
It's really remarkable. And I mean, I suppose you've kind of been around for long enough to know if this is true, but I mean, like, in terms of like executive compensation, like, have you noticed any changes in Germany with, executives, sort of really ramping up their salary? I mean, how do they get away with that? I mean, why do investors and stakeholders tolerate this? I mean, where's the actual return for the people that's, on the other end?
And because it's all of the same bunch. Because the guy who has a saying are a few executives from banks and securities. No? So what do you expect? Who's on the board? No? And they buy the guys from the unions, and that's it. No? If you have been a week to Mexico, you understand how that works. No?
So I've been told, because like the business partners in my company are like, oh yeah, I mean in Mexico it's a totally different way of doing business.
Exactly.
Even with the mafiosos and you come in that way, and it's just a totally different way of doing business. It's interesting. I'm not sure I got the stomach for the business side of business.
You see, I think a university is always a small universe where you can see things, no? And you see how things don't work really here, no?
Yeah.
How they're not, how when people start getting paid for organizing things get disorganized. Because then always someone wants to have the saying who is not really engaged in that. And I haven't, it's in the small, it's in the big, no? We have, for example, we have a European Parliament and we have a European Commission. Now, what the hell is the task of the European Union? It's only to coordinate and to initiate cooperation between the different countries. That's it. Why do we need to give decision making to the European agencies? We know they're inefficient. No? Don't we have enough people in government who like to travel? Well, you laugh, no? I don't doubt that, no? So it's once I was on a technical committee for the European norming and wastewater disinfection, and of course it was nice, no? We met once in Oslo. I've never been before in Oslo. Then we met in Valladolid, since I speak pretty well Spanish, and my Spanish colleagues. There were so many people, so there were 2 Spanish colleagues, and it was too many, so we split them up in 3 groups. Since I was Spanish speaking, I got the 3rd group, no? And then when everybody went to bed, we 3, had to plan the next day. No? For me, it was nice because I had contact to the Spanish people there, and was more involved in all this kind of stuff. And but of course, you don't really need anybody from outside coordinating that, telling you what to do. They're all grown-up people. They normally do what they do. And we all made our papers and coordinated the papers and got something done. No? So really nobody, and then later, they start trying to harmonize that, That's what can they do? They can just say, you know, the how do you say the table of content is not equally structured in all the papers. No, it's not, because it's different topics.
Yeah.
It's not important. No? Well, to them, they have no other possibility to contribute. No? You know, so now the hassle starts. They say this has to be all the same. No? So you rewrite all those. They just make disorder. No? Everything was fine until, you know, it finally started to get into the European offices. No? Then you got responses and said, and then you know, I gave it up halfway because then someone else took it over. No? And the paper that finally came out, I think nobody can understand it anymore.
Oh, God, it's just, what a mess.
So it was a good project. Started with euphoria and ended up with, you know, tearing away the usable documents.
Maybe we should start. It's almost 10 past.
Okay.
Yeah.
Well, then welcome everybody to the second day of this intensive course. Yesterday can you, yes, I have it here.
Okay, cool. All right.
Okay. Can anybody see me here? Or is that okay when I sit here, or
Yeah, maybe, well,
do you want me to stand up, or?
yeah, maybe stand up.
Okay.
For as long as you're comfortable doing so.
Yeah, no problem. So yesterday we talked a little about general things. I introduced a little bit the process of planning and and a little bit an overview of what chemical engineering is all about. And please recall, the chemical engineering is structured in mechanical processes, thermal processes, and chemical processes. Then we went on and that's important, what is the method of working in developing a process. You make it either by educated trial and error. This is when you want to invent something artificially. This you have mostly in refining mineral resources. If you take them out of, if it's mining, if it's metals, or if it's crude oil, and make all this organic chemistry, then you just don't have anything you can copy. But more in food, especially in food and pharmaceutical science, it's more general to just copy the nature and try to accelerate and make nature, make larger quantities, get higher efficiencies, and get higher efficiency also with the throughput per volume. Okay, now we get into the wastewater, what is really the example, because the entire course I want to show you how when you work in process engineering, how with some basic knowledge and with a lot of common sense, you solve your problems. This is what the course is about. And the example where we show this, how to apply this method, is wastewater treatment. In wastewater treatment, in this course, we focus a little bit on the domestic wastewater because that's the one where most is generated in the world. Every person, about anywhere between 100 and 300 liters a day, is producing that wastewater. And the composition is also well known because humans are biocatalysts, living biocatalysts on two legs, and they eat food and come out with the rest of it. And that's pretty much like I told you yesterday, when you work, you know, chemical reactions can either be under forced reaction conditions, that's with high temperatures and pressures, and then you have all kinds of byproducts, but also for this biocatalyst human being is also very selective. So he eats food, all kinds of different food, from animals, from vegetables, all of different resources, and the output is pretty uniform in quantity and quality. And this is what makes up domestic wastewater, and we all wash us, and we all have the same detergents, almost. There has been a change back in the 80s when we got away from the phosphates for complexing the calcium, the hardness in the water. But that's probably the only change in the last 50 years. Everything else stayed the same, and we're all using close products, although we live in very different parts of the world. Okay, now what is a problem? That was the end and the last question yesterday. What is the problem, or what are the problems for wastewater for the environment? Why don't you just discharge it? I told you in Kaohsiung in Taiwan, it was the city at that time was a city with 1.5 million. It has almost doubled to 3 million people now. And at that time, the Love River, you could smell the wastewater, and that's what you can do. You can just dump the wastewater in your rivers, and then just stay away from the rivers, no? If you want that. So wastewater treatment is a political decision. Do you want it, or do you don't want it? Because of course you can make drinking water. You can put the money in making out of dirty water drinking water, or you can put the money in making out of wastewater decent, also to get the pollution out of there and have rivers, and then it's of course a lot easier to make out of that clean rivers drinking water. Both options you have. That's a political decision. Probably, I believe, but nobody proved it up to now. I believe, however, that treating the wastewater, having clean rivers, besides that you can enjoy the nature, which I estimate as a high value, I think it's probably also more feasible to treat the wastewater and have less effort in producing drinking water. But in future, and to be honest, this might change a little bit, because when the glaciers in the Himalaya are going to melt down, what are we going to do? There's 3 billion people living from that water. I can imagine that, for example, they're flushing the toilets in coastal areas. Why don't we use salt water for that? What's the reason to use sweet water for that? No? Maybe in 20 years, at least in coastal areas, our water as a red of drinking water is not going to be drinking water, it's going to be salt water. And maybe in every household you have a small unit of reverse osmosis, and you produce those 3 liters per person which you use for drinking and cooking. You make that in desalination. Might be an option, no? Okay, I just want to give you the idea that there is going to be a lot of change in the next 20, 30 years in water economy. So it's going to be a very interesting field. How are you going to work with all this? Because climate change is going to affect our water economy significantly. Although, and this is a different source, is when you today already look at countries with water scarceness, what is it? If there's no water, arid zones, no?
Yeah, deserts.
Yeah, if you look at arid zones, I did that once in North Africa and Arabian countries, and I thought, because at that time, back in the 80s, I was in wastewater disinfection, and I thought that reusing the water from the shower for flushing the toilets would be a good idea, and maybe make life easier in those arid countries. But then you find out that in those countries, 70 to 90% of the water is used in agriculture. And the water we use in agriculture is at least 10 times or more. It's much more than 10 times the water we use in the household. And right now we just don't really realize that, how much water we use for producing food. So that's a totally different story. So, it's not that easy, but for at least for domestic water, there's going to be different views, and that's besides the climate crisis and the energy. Water is the next important problem which we have, no? Because without water, there's no life. But okay, let's get back to things. Let's get back on the sound ground. Where we stand today, that we can teach something, that we know what it is and don't do prognosis for the future, which are always a little bit of problem because it's for the future. Nobody knows what's going to happen exactly. So what are the problems of wastewater for the environment today? And let's talk about domestic wastewater. Okay, they are listed there in your text. One is the Curies particles from food and sanitary articles that remain as waste on the banks of the receiving water bodies. No? You can see that in some city ditches when we have overflow, stormwater overflow. Some of the communities have started to have sieves or have sedimentation tanks for stormwater in order to cope with that problem. But what do we do on the wastewater treatment plant to eliminate those corrosive particles? The second thing is, in the wastewater, of course, we have settleable organic matter that forms sediments in the receiving water bodies and causes an uptake of dissolved oxygen, and that might form hydrogen sulfide if it's degraded anaerobically. And this is very toxic to fishes, and it happens if you have those sediments. If you have then stormwater, those sediments are remixed, and then you have very intensive oxygen depletion in your receiving water, and you're going to have fish dying in a major scale. We experienced that once in the river Isar, because in some years, because of the effluent in dry weather is pretty low, because they took a lot of the water from the river Isar through a channel to make hydropower. So the effluent in dry weather conditions in the river that remained, that was not used for hydropower, was pretty low. So we had sedimentation of settleable matter from the different sewage treatment plants, the rest that went in there. And that accumulated in the years, and then we had stormwater. Of course, the stormwater, the channel for hydropower always takes the same amount of water. So the flow in the river increased dramatically due to the stormwater. And of course, some of the sediments were remixed. And then we had for 30 kilometers, all the fish were dead. It was about 5 tons of dead fish we had to get out of the river. And from one treatment plant in Grüneck, which is just behind the city of Munich, it was claimed that the operators discharged 1,000 cubic meter of sewage sludge into the river because they had no other explanation at first hand for this fish dying. So the manager and the main operator were arrested, and I had to go for 1 week into jail to be examined what they did. So it took us 1 week because at that time I was making my PhD at the University of Munich, and I was in sewage sludge. So I had the task to prove that if there was guilt or non-guilt of those people. Right, so I went to the treatment plant of Grüneck, and of course I measured the temperature because the digester has a temperature of 39 degrees centigrade. And then I asked a question, as it still had 39 degrees centigrade, where did you get those 1,000 cubic meter of 39 degrees water from? With nobody realizing that. Where did you get, how did you keep up the solids in the digester if you release 1,000 cubic meter? Where do you get those 1,000 cubic meter from? Okay, the 1,000 cubic meter you can get out of your aeration tank, but how do you get it warm, and how do you get the solids, and how do you get the ignition loss? That's because the ignition loss in digested sludge is, of course, much lower than in activated sludge. How do you keep all those parameters? But it took me 1 week to convince the judge to free those people, because it was totally impossible. Even if you would have taken the sludge from another sewage treatment plant, 1,000 cubic meters, how many trucks is that? Tons, no? So it's 100 trucks. Nobody realizes that in a small village, when in one night 100 trucks, 10-ton trucks pass through the village. Pretty impossible, huh? Okay, you're just telling you, Okay, this settled matter has also to be eliminated because the oxygen, the dissolved oxygen content in the freezing water is really the main parameter we focus on in order to keep the receiving water in a good ecological state. Okay, what else do we have to do? We have organic suspended and dissolved organic pollutants, which we measure with COD and BOD, because this is what happens when we release those in the receiving water. They will also deplete the dissolved oxygen content when they're degraded by aerobic microorganisms. And last but not least, we have to deal with the nutrients, nitrogen and phosphate, because in our urine we have, urine will dissociate into ammonia and hydrocarbonate, and that's a source where most of the ammonia comes from. And then also we have in our feces and in our urine we have some phosphates. These are nutrients, and if those nutrients are in the receiving water and you have sun, you're going to have algae growth, and the algae growth, I mentioned that yesterday also. During the day, it's fantastic because when you have algae growth, that means photosynthesis, so you produce oxygen, you will have oxygen saturation, but at night when the sun is gone, these algae will be degraded by microorganisms, and then you will have respiration, and the dissolved oxygen content will be depleted, and your fishes will die during the night, and unfortunately they will not revive during the day. No? Because once dead is always dead. No? Okay, so this is the points. This is again a method which we have applied here. We have looked at what problems do we have. That's a way of working structured. We have to look at the different classes, and the criteria here was that we have looked at the different type of solids we have in the wastewater. We have some which we can't grab, which are dissolved, so they are not accessible with mechanical processes, separation processes, because mechanical separation processes only can influence the dispersivity of multi-phase, multi-component systems. We have here multi-component, multi-phase system. We have solids in the wastewater, and solids of very different size, distribution, and density. And we have a continuous phase, which is our water. No? And then we have in the water, we have also dissolved components, which form just one phase with the water. But first of all, we look at what we can do with mechanical processes, because always when you have to treat something, is always mechanical processes are cheaper than physico-chemical processes like flocculation or whatever you can do, and they are cheaper than thermal processes, and they are cheaper than chemical process. Thermal process would be evaporation, distillation, and so on, and chemical processes would be advanced oxidation processes. Oh, sorry, in between is, after mechanical comes, of course, biological. Microbiological processes are the second cheapest. And this is what we're going to look at. First, we're going to look what we can do with mechanical processes. Secondly, we're going to go what can we copy from nature and do with microbiological, biological processes. Third of all, if none of that applies, then we have to go the hard way and go into physical-chemical processes, which is that we have to buy chemicals, be it flocculants, be it flocculants precipitation, be it organic flocculants for increasing the floc sizes. This is always more costly than aeration or anything you can do in biological systems. And if that doesn't work, then you're in a very hard problem and very costly, and you have to think about thermal treatment or advanced oxidation processes. Okay, now Curet's particles can be separated from the wastewater by a Curet's filtration with a bar screen. Separable matter can be separated from the wastewater by sedimentation in a pre-sedimentation tank. Organic suspended matter and dissolved organic pollutants can be eliminated from the wastewater by aerobic degradation in an activated sludge plant or in a trickling filter. Nutrients are incorporated in the surplus sludge growing in the activated sludge or in the trickling filter process. As nutrients in domestic wastewater, however, are present in excess of the assimilation in the surplus sludge, special microbiological processes, nitrification, denitrification, and biological phosphorus elimination, or physical-chemical processes, chemical phosphorus passivation have to be employed in order to extensively eliminate nutrients from domestic wastewater. This is a little bit the solution before we discuss how we come up to the solution. And now the figure 1, which you see on the screen here, shows the process scheme of the current standard of a mechanical biological wastewater treatment plant with an activated sludge system and extensive nutrient elimination with nitrification, denitrification, and biological P removal in mainstream. And you see first here, you see we have here a screen, then we have a grit trap, then we have a pre-sedimentation, and then we have an anaerobic tank for biological phosphorus release. Then we have the denitrification tank. And in order to have any nitrate to denitrify, we have to have a recirculation of the nitrate which we form in the nitrification tank. And finally, we have a secondary clarifier where we separate the microorganism from the now treated water, and we have to recycle the sludge in order to decouple the hydraulic retention time and the SRT, the solid retention time. That means because the microorganisms do not grow that fast, and that's good they don't grow that fast, because if they would grow that fast, we would drown in surplus sludge. And we don't want to drown in surplus sludge, so, but we have to keep the microorganisms in the system. That's why we have to separate them and recycle them, or we have to fix them on a carrier. This is now all a little bit, and that was a quick run, a very quick run. And now let's look at the things. How do we get to those decisions that are preferable processes? Why do we use a screen for the corrosion? Why do we use a grit trap for the sand? Why do we use, and why don't we use air filtration? Why do we use a pre-sedimentation and not a filtration? And how does the biological system works? That's a second step when you use after treating a little bit the mechanical separation processes. Okay, now the screen goods are incinerated in waste and incineration plants. The washed sand is used in civil works like road construction. Primary and surplus sludge are anaerobically stabilized in sewer sludge digesters in large treatment plants and are aerobically stabilized in extended aeration in small wastewater treatment plants. The aerobic stabilization you might know from composting. You might use that for solid waste in your house. The stabilized sewer sludge shall be dewatered, dried, and now incinerated, which is a sad story because we just have to incinerate it because it's so contaminated with pharmaceuticals, and it used to be heavy metals. I think heavy metals we have pretty much under control in at least in Germany and other European countries in North America, because we control our industry pretty strictly. In other countries where you don't do that, we had to learn that in the 1960s to 1980s, that we have indirect discharge control, and that everybody who works with heavy metals we look very closely at, and we have pre-treatments in those plants where we eliminate those heavy metals by precipitation processes. And those heavy metals that we still have in our domestic wastewater, they come from all our metal tubes for the drinking water, and that's mainly copper and zinc. And this is also trace metals for the plants to grow, and they are even in deficit in some regions in Germany. So In some regions, the farmers are almost happy if they get a little bit copper and zinc, because they need that in their soil. So there, it's more or less, it's if you just apply certain amounts of digested sewage sludge, as it contains the nutrients, nitrogen and phosphate, it has been used for a long time, since at least more than 200 years, in the form of fertilizer. But of course, you don't want your anti-baby pill when you brush your teeth, because then humanity is going to die out because everybody, if he gets his anti-baby pill when he brushes his teeth, we're not going to get any babies anymore. So that's a little bit of risk where a lot of people's heart disease. You can't say you can't use your medication for your heart disease. Go and get you some wood and go to the crematorium. This is not really a social and answer to that problem. So yes, we do need our medication, but we have to keep this medication out of the nutrition cycle. And for that reason, in Germany, we decided that all the sludge shall be incinerated.
Just out of curiosity, because I mean, we obviously use a lot of halogenated pharmaceutical products. When you incinerate halogenated molecules, you of course end up with all sorts of nasty ozone-depleting chemicals. How are those scrubbed out during the incineration process? Because obviously you can't control what goes in so easily. So how do you take care of that on the back end?
I think also in the last 20 years in incineration processes, the oven is only maybe 10% of the cost of an incineration plant. 90% is waste gas treatment. And I think waste gas treatment by filters, and also the control of the incineration process, that we have a complete mineralization in the incineration, is now well done, because you have those regulations where you have to have, I think it's at least 3 seconds at 1,000 degrees, and no organic molecule is you have really a 99% oxidation there. And then all the NOx and SOx, they are washed out, and with catalysts they're reduced. So this is under well control, and there are online measurements, and also acidic stuff like hydrochloric acid is washed out. Of course, all this Seveso stuff, the dioxins are controlled. We have those online measurements in Germany. You can see it on the internet. You can see, because they publish, so they have to publish this online, their online controls, and so I think there has been done a lot. I'm not the expert. If there is still anything that shall worry us, I think it's you can just guarantee it by temperature and residence time and oxygen. There you can say that there's no organic survives the incineration process. And then you have just to deal with very basic molecules which we know, no? Yeah. NOx, SOx, and hydrochloride, chlorine, and that's it, no? Because you're not going to have any hydrogen sulfate that's burned, no?
Yeah, exactly. Okay.
Ammonia, it's all oxidized, no? This is the only way how the incineration at high temperatures and controlled is really a process where really knock it down. It always comes up, to optimize the energy usage of that thing, and to go into pyrolysis. No, and I think whatever I heard of pyrolysis in the last 30, 40 years since I'm in business, it has always been. There's no positive result out of that. And I was once in the Ukraine, in the southwestern part of the Ukraine. There's a mountain range. They basically live off good water, what they sell, especially to Arabian countries, as bottled water, and they wood. And they have a lot of wood. In the wood, they made a lot of charcoal. So there was an old At Soviet times, it was a big chemical combinate, also a big chemical factory. You saw all those halls, maybe 200 meters long, 60 meters wide, 18 meters high, or whatsoever, full of old installations, all stainless steel. No, it was really $1 million baby you had there if they would clean out the stainless steel there. And but it was all just standing still and running for the end. The only plant that was still operating was 7 or 8 pyrolysis plant out of the year 1787, and it was still KUK. Then that's the old Austrian, nicht Kaiser und Königlich, Hungary and Austria. Was casted steel. Was tubes maybe 3 meters in diameter and 20 meters long, and they were pushing. It was like rowing boats, no? And they were full of wood. You put all the wood in. You shovel them. You push them in. You close really those big lids, and then you start it with gas. That was pyrolysis gas. They saved in one storage tank there. And then you produce again pyrolysis gas, comes out charcoal, and there was about bags of all our German Baumarkt. You know what a Baumarkt is?
No.
That's where the do-it-yourself stuff for doing work in your house, where you can buy tools, nails, and everything. And those shops, how do you call them?
Hardware stores.
Hardware stores, no?
Yeah.
Okay, all those hardware store chains in Germany, I saw all those bags, Praktika, Baumarkt, all known to me in Germany. They were packing, basically for most of the German market, they were producing the charcoal there, which we use in our grill season in the summer. And if you ever started a grill, you know what you do. You put the charcoal on, you heat it up, and you go away. No? Because the first 15 minutes, you don't want it to be there, because it's... You see all the contaminants coming out there. What happens while producing from the wood, and wood is a pretty nice product, a pretty nice raw material. You know what it is chemically, and it's basically only and almost only carbohydrates in a different chain length. No? It's lignin, cellulose, hemicellulose, but pretty clean stuff. Almost no nitrogen, no phosphate, no troublesome molecules you have in there. And pyrolysis, when you do that, you get those tars and all this kind of stuff, which is ugly. And some of it, and not only some of it, but it's a considerable quantity, will end up, because if you make a pyrolysis of carbohydrates, what do you get? What do you get? Charcoal. And else? Charcoal is not the main product. What is the main product of pyrolysis? No. Now, what comes out when you make out of carbohydrates? You make charcoal. Charcoal is what?
It's carbon.
Carbon.
Just carbon. So
Okay. And what's left over when you make?
a lot of oxygen, a lot of hydrogen, so water.
Yes.
Yeah.
How much water is it?
What would that be? 6 moles per mole glucose.
How much is it?
That's a lot of water.
It's 6 times 18.
Yeah.
Or you can break it down easy and make it just one. Maybe any carbohydrate has a formula CH2ON. So CH2O, what's the molecular weight of that?
12 plus 32?
30.
34.
30.
30. Okay.
12 and 18.
Yeah. That's, wow.
Easy. So 30. No? And how much of it is water? 18.
1802.
Now-
Yeah.
So now you can divide that. So it's, if you make it by percentage, no? 18 from 30, you can divide by 6. So it's 3 fifths. And 3 fifths is 6/10. 60% is water. So now what is in wood? Wood is what? Wood is carbohydrate, and what else is it?
Of course, lignin, a little bit of protein, very small traces of fat, some macronutrients.
No, it's water,
Well,
basically.
yeah, mostly water. It's hydrated water.
No,
Hydrated
you have hydrocarbonate, and then you have moisture. Now, if you get wood, it has at least, as if you cut wood fresh, you have 50% of water and 50% of wood. And wood is 90% of carbohydrates. Now, and if you dry it, you still have 20, it's V20 they call it, you still have 20% is pure water, is moisture. And then you have this carbohydrate. So you have at least, when you make a pyrolysis, no, you get, I think it's 72% of water when you have dry wood, and the rest of it is charcoal, and then you have close to 0%, but very ugly substances. No? But this is, we come later back to this, because in microbiology, what do you have? You have carbohydrates, you have proteins, and you have lipids. And quantitatively, the rest as an engineer is just a joke and a half. No? It's less than you look at. No? So it's, you normally do not consider all these important things like enzymes, minerals. For as a process engineer, it's side products. It's nothing of importance.
Cells are 70% water, most of them.
Yeah.
It's all water.
It's all water. No? Okay. So when you because I had also a colleague who was teaching in our school processes of renewable material, and he was also very fond of this pyrolysis process. So when I'm asking, what do you do with water? He said, oh, it's only a little bit vapor. I said, no, it's not a little bit vapor. It's 70% of the mass. He didn't believe me. It took him a long time, but this has nothing to do with believing. It's simple. It's fact. No? In this 70%, so when I asked in this plant whether we're operating those pyrolysis plants, I asked, where's the water? He said, yes, there's a small pipe going out. Well, this pipe had just a diameter of 150, 200 millimeters, not that big, no? But it was flowing out of there, at least 20 cubic per hour. Now, they loaded maybe 100 tons a day of wood. Now, out of those 100 tons, 70 tons of water is only 3 hours, 20 cubic meter per hour. So it's, it's not that. But then we went, I said, where ends this pipe? Oh, it's a small ditch there. So we went to this ditch, and this ditch had maybe a flow of 3-4 cubic meter per hour. It was meter 50 wide or 2 meters wide, 30 centimeters deep, and was flowing with 1 meter per second or something. So, just a nice sized ditch. And this pipe went in. So if you looked upstream, you saw a jungle, more or less plants and everything. If you looked downstream from the bridge, there was 3 meters to the left and to the right side. You saw pure rocks if they were cleaned with a toothbrush. No? There was not one living microorganism, nothing. Then I asked this guy, what do you think is the contamination of this yeast they call this liquor from the pyrolysis process, water? No? What is the contamination? He said, it's none. It's not really contaminated. We measure BOD as 0. I said, oh, I believe that. No? How about the COD? We said, oh, it's 600. 600 doesn't really sound much. But this is also something you got to know when you go to a foreign country. Those tubes you measure COD, they are limited to 600, most of them. So they just didn't look that it was in excess. I said, did you ever dilute it, the moisture? No, we don't dilute it. No. I said, okay, that's very interesting. So it can be 60,000. You wouldn't know. No? You just know it's 600 or more.
But isn't the standard protocol, if you have a value over 200 milligrams per liter COD, to do a 1 to 10 dilution?
Yeah, you should.
I thought that was just standard practice.
Yeah, if you know what you're doing, yes. But if you're not really interested in finding a contamination, it's very easy not to look at it. If you don't dilute it, you say it's 600. What's the problem? Sounds good, no?
So there's no regulatory agency coming back and be like, hey, you're...
Yeah, well, when I showed that to the inspector, he, of course, got a little bit conscious and said, shit, no, I haven't looked at that. I haven't... They were not really interested in finding it. And that was a guy from the lab, and the inspector is just an inspector for most administrative things. When this was why they got their experts from the European Union to unify the legislation in the Ukraine to the European Union because at all the transborder rivers, no? Because they want to make contracts for the transborder river, how they will administrate all the pollution into the rivers, no? And the Ukraine had they wanted different laws. They used to have the Soviet Union laws, and they want now to copy the European Union laws, no? To apply that to become modern countries because they wanted more economic cooperation with the European Union, and the European Union said if you want to get money, you have to apply our environmental standards, no? And this was why they sent this expert committees there, a bunch of them, no? And I was a member of one of those, no? So this was an interesting experience, and that's when I finally learned, leave the fingers of pyrolysis. It's a process with so many side byproducts that you have no chance of ever getting any control of that. No? This is like half pregnant. It just doesn't work. Either you're pregnant or you're not. No? It's just something that doesn't work. Either you do an incineration, and then you do an incineration, you do it until everything is incinerated, or you just don't do it. Then you do a pure biological process, but anything in between is not a solution. It just definitely is not. No? Whoever tells you anything else is lying. Okay, I have a very clear position on that. Okay, now let's come back because this is also because if you have effluents if you have effluents out of the process, you of course need to know, I have a solution, what do you do with those effluents? Now, I recently had an inquiry from a young colleague out of Peru, and they have in a cannery, a vegetable cannery factory, they have a process that they have a biological process, I think, and they claim they have too many oils and fats out of the paprika. Paprika, you know what that is? Those, same word in English, I hope, no?
Peppers? The bell peppers. Paprika, like peppers. Yeah,
peppers. Okay. Peppers, and they have it from one other vegetable they manage in large quantities. They claim they have too many oils and fats there in the wastewater, and so they want to install a DAF. They wanted, of course, they didn't want to buy it externally. They want to do it internally. So I asked them, well, do you need a chemical conditioning? Because this is, you need, if you have an emulsion, you just don't get to the fats by the, you got to break the emulsion in order first, and then you need a chemical conditioning with iron or aluminum salts in order that you can flotate the fats, or are they free fats? I wouldn't know. So I said that's the first question I want to answer. And the second question is, if you put a DAF, what do you do with the sludge from the DAF? No? Do you have anywhere a biogas plant to digest where you can get rid of that? Because if you have that stuff, what are you going to do with it? If you do not need any chemicals, you might be able to mix it into animal fodder or something. But if you have to add any chemicals, you need a digester or something, no? So and that's the expensive part. The DAF is the easy part. No? So you have to find. So this is why at least I'm so fair to tell you what happens with these effluents. But now let's get back to the processes, which is where I want to show you the methodology of cleaning that. Mechanical separation processes are employed to separate coarse particle, sand, primary, and activated sludge from the wastewater. In all these cases, we have a system of particles dispersed in a liquid fluid, no? Which is our water. Now, in order to design a mechanical separation process appropriate, the relevant characteristics of the dispersed and the continuous phase have to be described. Well, how do you do that?
I mean, depends on what you know. I mean, total solids, conductivity.
What do you do with conductivity?
I usually correlate it to total suspended solids, TDS.
But conductivity has something just to do with salts, and salts are in solution. That's ions. It's an ion concentration. Can you do anything with mechanical separation with ions which are in solution?
God, no.
No. So that's not really an interesting characteristic. But what are interesting characteristics? Okay, skip that class. No? If you were in that class, you would have known separation processes. What unit processes can we apply? There's not that many. What options do we have?
Chopping, milling, I mean, you're talking about like.
No, you want to separate them.
Filtration.
Okay, you wear filtration, sedimentation. Okay, and that's it.
Yeah.
There's no more. So you just have to decide in filtration or sedimentation. In sedimentation, you still have two options, gravity or centrifugal. In centrifugal, you have two options, cyclones or centrifuge. I like to show that in trees, no? So if we talk, can I write on this?
Oh, yeah.
Can you see that? Oh, okay, no? So if you want separation of particles, no? Out of liquid, it's definitely a mechanical separation process. No, that's it, because we have a two-phase system and we want to separate the concentration of the phases. It's a dispersivity problem, so it's mechanical separation. Okay, what unit operations are unit processes? There's just two, is filtration and sedimentation. Well, how do we go about in finding out which one we are going to use?
Well, the first thing I suppose I want to know is a little bit more about what's suspended. I mean, what's its density, what's its size.
Okay, now we get to this is characteristics that we need. We need this particle size distribution. We need the concentration. We need the density of the liquid, of the fluid, and we need the density of the particles. We might need the shape, a form factor for the particles. No? This is all characteristics. And then there's a nice equation from a British guy. His name is, what is the equation, was mostly used in sedimentation. Probably all of you have had that in some class.
Yeah, I've definitely had it. I don't remember the name of the
The
equation.
name is Stokes.
Stokes' law.
Stokes' law is no, Stokes' law, however, is only the one for laminar conditions. No, if you expand that, you get and this is just equilibrium of forces. It's a gravity force that makes the sinking velocity of the particle and the hydrodynamic resistance that later determines the sinking velocity of a particle in a fluid that doesn't, on a fluid not flowing, as in a fluid in Ruhe, as it's calm.
Yeah.
No? And so Stokes' law is ideal. It applies normally for spherical particles of the same size and whatever. And this formula, of course, is now a little bit difficult because normally we just don't have, our fluid is flowing, so it's not calm. Our particles are not uniform size, and they are not spherical. And sometimes, if we talk about flux, we just don't know the particle size and we don't know the density. And this is now when you become in engineering, where you have a combination of basic physical chemical laws, or the natural laws, and empirical knowledge. This is why people have done that before, have studied, and have found out a lot of characteristics that and have made diagrams. And this is the empirical knowledge, and you can use also these empirical equations. Empirical equations, you can realize that normally the dimensions don't square well, and you have odd factors in them. Then you know it's an empirical equation. Okay, now we have characteristics. Characteristics. We have here our fluid. That's density. And one more parameter for our fluid that's important, which we haven't named so far. Viscosity, obviously.
Yeah.
No? And then we have our particles. Form. What else that we had? Shear strengths. What do I mean by that?
Don't deal with shear, so I don't know.
Well, if you have a nucleus from a cherry,
The what for maturity?
a cherry has a stone inside,
Yeah,
no?
the pit, yeah.
Pit. Do you think it has a high shear strength or it has low shear strength?
Probably a high shear strength.
And if you have activated sludge flocks, do they have the same shear
It
strength?
would be lower.
Does it have any influence on your choice, filtration, sedimentation?
I would imagine so. I mean, I suppose with the high shear strength material, you'd probably go for filtration, whereas with low shear strength material, you're going to go reach for sedimentation.
Okay. And this is what's written in my text. So you can deduce that by your own intelligence, right?
It seems like
It's obviously true, no? And this is what I tell you. If you have a little bit an idea of basics, if you know at least if you know how to qualify characteristics, this is what you have to learn in lessons and basic lessons and physics and chemistry lessons. You have to know what is density, what is viscosity. You have to know the influence, which is also you can imagine that a particle with a high density in a liquid will have, of course, a high sedimentation velocity than a particle of the same size with a low density. But, and this is again a problem, if I want to separate small particles with a high density and at the same time I have big particles with a lower density, that might be shit, no? Because then both of them might have the same sinking velocity. So sedimentation is there not a process to separate those two? And filtration will not work either. So I have to think how I deal with that. Okay? So first of all, when we talk now about the Corrèze material, what do we talk about? We talk about cherry pits, we talk about hygienic articles. So in general, we talk about particles with a high or low shear strength.
high shear strength.
High shear strength.
So just to be clear, these particles that we're talking about are large particles. Would you say greater than half a centimeter in size? Is that coarse enough? I mean, where do we draw the line between a coarse material and a fine material?
The practice is later. We have screens with 3 millimeters diameter. Now, if you of course, you accumulate screen goods, and with the screen goods, of course, the separation diameter gets smaller, right?
Yeah.
When you clean the screen, at the first moment, you have only 3 millimeter particles will be retained. But then, if you have a bed on it, almost everything shall be retained.
Yeah.
No? So this is again, and this is also a thing we have to consider, and we have to talk about how we deal with that, because this is always a problem in wastewater treatment, because all over the thing we have our feces, And the feces are not, you don't really want to don't deal with them. You know, you want to have them, the feces is something you want to end up, that shall end up in the digester. Because after it's digested, it doesn't stink anymore, it's hygienically not any problem. But I don't want to separate it, I don't want to have it in my screen goods, I don't want to have it in my sand. Because I have to do something with the screen goods. I have to dewater them. I have to transport them to the ignition, to the incineration plant, and nobody at the different places where you store it and we have to have it wants the pure shit in it, because it starts to stink. Right? It has odor emissions. It's hygienically a problem, and it's aesthetically a problem. So this is things you have to find a solution. But basically, in the corrosive material, and this is what you find here in the text later. So just a minute, not to lose the thread, let me just, because this is here, I have written it, and the way I normally, because not to lose important ideas, I like to look at my text first and present you that to finish this discussion. But you see, if you think by your own thinking, if you know, if you've all learned this, you have all heard this, this is nothing that you have never heard of, and this is something you can work with in your brain. You just got to have it present in order to use it as an engineer. And this is how structured work is. We know, make a tree of our sediment, of our unit processes, and then we have to see what is the strengths of the options which we have. And it's totally right. The filtration is always something you should think about when you have particles with a high shear strength. You don't need to think about it if your particles, if your dispersed phase has no shear strength. If you have flocks, then you're just going to have a problem with filtration. Then you rather tend to sedimentation. When you have high difference in density, you will tend, sedimentation is obviously an option, because it's going to think, you can have a high rate of, you're going to use a low volume or a low small surface area will be sufficient for separating this. For sand and water will separate perfectly. No? Then in filtration, you don't want to have very small particles, because then the filter is gonna be closed rather soon. It's going to be verstopft. It's clogged. Yeah, right, clogged as well. It's going to clog very fast. No? Clogging is a problem of filtration. It's not a problem of sedimentation. So, just by things you basically know. And if you have all particles of the same size, if you have pretty uniform size, it's good for filtration. If you have particles with a wide particle distribution, it's always that the small particles are going to fill in the gaps between the big parties, and you're going to get a filtration layer that is like a brick, so no water is going to go through it, so that's not good for filtration. So it's very easy to find those criteria, and then you just have to see what is the criteria, a list, and that is by this list of criteria and how important they are. Morphologic box. That's the word we looked yesterday. Here you can work with morphologic boxes because it has nothing to do with money. So you can't really quantify it, but you can say this is advantages or it has a disadvantages. From those morphologic boxes, you can see which of the unit processes might be more appropriate. Well, and of course, in today, there's nothing that has not been done almost. So you can also look what is the experience with the things. No? But okay, let's get back to the text here shortly, so we don't. As in order to design a mechanical separation process, the relevant characteristic of the dispersed and the continuous phase have to be described. Okay, we looked at those. Most relevant characteristics of the dispersed phase are density of the particles in comparison to the density of the continuous phase, particle size distribution, and shear strength of the particles. Most important characteristics of the continuous phase are the density of the fluid in comparison to the density of the particles and the rheological properties. No, I forgot an E here, and I forgot an S in my particles. No, okay, we can't do that. No? Never mind.
I'll be back in 30 minutes.
Okay, thank you very much.
You got 3 people on Zoom.
Oh, okay. So I will continue here for 20 more minutes, and then we'll also make a break of 15 minutes, because then we had 1.5 hours, and I think after 1.5 hours, attention will decrease a little bit. Okay, and now you see the next, this is what we also worked out. This is what is written here on the whiteboard. And now we look at the screens for removing the Kurau's particles from wastewater. The Kurau's particles in wastewater can have a density below or above or close to the density of water. Because if we can have particles of styropor from packings that got in the wastewater, or fat chunks or grease chunks, and these all have a density below or close to water, so they floatate, or they might floatate in the water, or they might swim up to the surface of the water. And we have those cherry pits and other things that do have a high velocity that have a higher density of water and will sink rather fast. So sedimentation is excluded because we just have not a uniform difference of density. And that makes sedimentation not an easy process. Just if we have a difference in density we have to have in order to apply sedimentation. If we would have just particles with a density well below the density of water and well above the density of water, we could have also sedimentation, and we can take the sludge from the ground of our sedimentation tank. That's the particles that have a higher density, and we can skim off the surface and take out the particles with lower density of water. And this is actually what we do in a grit chamber, where we separate the sand and the fats from the water, which stays in the middle. But in a Kurau screen, where we have all kinds of density and a lot of particles, plastic particles, which have almost the same density as water, there, of course, we use filtration. No? Also Kurau's particles. Just a second here. Kurau's. Density of water and shear strengths, filtration. No? Okay. In Kurau's particles, due to density above and below the density of water, of the particles, and the high particle shear strengths, we favor filtration. Okay, let me tell you this now. Kurau's particles in wastewater have a density below and above and close to the density of water, which is a liquid in the liquid fluid in our system. The particle size range from something maybe even a little bit smaller than a cherry stone to Q-tips, sanitary towels, up to rubber boots. No, sometimes it's incredible. In Paris, there's a museum about the things they got out of the sewer system. Okay, Paris is a city with 9 million inhabitants, and they used to have one central wastewater treatment plant in Archea. There's 5 treatment plants next to each other with a capacity of 9 million in PE. It's a real big wastewater treatment plant. They have a sewer below the River Seine, has a diameter of 3.50 meters, and they have a stone ball of also this diameter, and this is how they wash out all the sediments and the stuff that's settled in the channel. They roll this ball, or they have it swum by water through this huge round channel below the Seine, the River Seine, and then they take this out, and then everything comes crushed out. There has been, at least in the sewer system in Hamburg, there's tours with a little boat that you can tour the sewer system in Hamburg in some parts. The old sewer system, they are all made out of brick stones, and they are almost as big, also 2 meters wide and 3 meters wide, 2 meters high. So it's easy sitting in a boat that you can just tour on these sewer channels. Because they are, of course, they are only filled when you have stormwater. If you have dry weather flow, they're normally not filled. Of course, the one below this, the Seine, because it has to be filled, because it's like a U-shaped sewer. And out of the sewer in Paris, and same thing in Hamburg or Londres, they took out, I think, up to 100 bikes, and they almost got a complete tank, as a war tank, out of that stuff. No? It's incredible what you find. You find heads of cows, you find entire pigs, and I don't know whatsoever is in this museum, what they grabbed out of the sewer system. It's just, you can hardly imagine how people got that into the sewer. Because normally all the inlets into the sewer, at least in your house, your toilet is the biggest inlet in what you have in the sewer system. But even outside in the roads, you see where the rain in the streets might go into this mixed sewer system. But it's incredible how people get their bike into the sewer system. But it has been done because they are found there, not just one. Okay, and there are rubber boots, so you have, this is just a thing of a normal, almost normal. You find those in almost all kinds of cities, as shoes and all this kind of stuff. Entire, as clothes, coats, hats, and whatever. You find all this this is the big parts. There's not much of it, but it's there. Most of it is of course, all this sanitary products, small plastic parts. From food, of course, you have some leftovers. You know, if you make a salad, you might, the ends of your carrots or leaves might end up later. When you cook a soup and there's something over the rest of the soup, well, what do you do with it? You can't put it in the solid waste because it's too liquid. So most people will put it in the toilet and flush it away. This of course you will find later in the sewer, and this is what you have to separate. This is what it is when you talk about Curacas people. Just watch yourself, what you do in your household. Most of these particles have a high shear strength. The widely varied density makes separation by sedimentation or flotation difficult. Considerable minimal size and high shear strength of the particles, however, favor filtration with a screen for particle separation. And this is, what a surprise, the in practice applied technology. In the course of the last 70 years, column width, also the mesh size or pore size of the screens have been reduced from 10 to 20 millimeters, which was the fine screens. In former times, we used to have also Curacas screens with 10 centimeters between the columns, and has reduced today to 3 to 6 millimeters. This is the mesh size which we use today in order to get out all the Curacas particles from the wastewater. The improvement of screen efficiency and reliability in combination with improvement of grid chamber efficiency and reliability has reduced considerably problems with sediments and scum in anaerobic sewer sludge digesters. This is back in the 80s, when I started, for example, the wastewater treatment plant in Darmstadt, they have a mesh size or a bars, in between the bars, they have 15 to 20 millimeters in the two different bars they use. And the sewage sludge digester, they have to take out every fortnight, or every 2 weeks, they have to take out the scum layer from the digesters. Scum layer in those 2 weeks is anywhere between 15 to 30, 50 centimeters that's built up. So we're talking about maybe it's 4 digesters, so we talk about almost a truck, like 5 tons of this screen good, which they finally take out of at the end of the wastewater treatment plant, out of the sewage sludge digesters. In order to get that out of the sewage digesters, they have a door, a scum door, they call it, and they raise the level in the digester a little bit, and then they open the scum door and flush out this scum layer, because if you don't flush it out, if you flush it out, it breaks like ice breaks in different big particles, and when you flush them out, they get smaller, and this is how you can take them out, and you just push them, you just put them in a big truck and take them again over a screen, or you just let it, you put it on a sandy area, let it dry, and then you take it away to an incineration plant. But this, of course, is a lot of work. In the treatment plant in Wismar, where I have my lab, we have a screen of 6 millimeter, and in the last 20 years, we never had to use the scum door. This is the difference. And this is between 15 and 6 millimeter screens that makes a difference if you have scum or not in your digester. And you don't really want to have scum. You need to be experienced to work with the scum, and to open the scum door is always a little bit dangerous, because if you open a door when the door has maybe in Darmstadt it's 50 by 50 centimeters. The small one, in the big digester, is 70 by 50. And if that door swings open, that's when you open it from the hydrostatic pressure behind it, you don't want to be in between that and the wall. And we have rubber all over the place, because the door is made of metal, and if that gives in a spark and the biogas comes out, you can blow up the whole digester. This is a problem with removing the scum. The scum removal is not really something you want to have to do if you don't have any experience with it. That's something a little bit critical. There has not been many digesters blown up, but there have to be some because people really did idiotic things. No, they were going up and they opened the digesters and made some welding work there, or worked with tools that were not spark safe. You shouldn't do that on a digester or biogas plant. That's suicide, more or less. As well, and another thing you never do in a wastewater treatment plant, you never go below ground if you're not sure that there's sufficient oxygen and there's no hydrogen sulfide present. So never go into a sewer or into a vertical opening below ground if you're not sure, if you haven't measured the gas. No, don't do that. That's where most people get killed in operators from sewer systems. This is the most dangerous thing. So don't do that. And also with digesters, be careful not to have gas explode there, because it's an ugly thing. No? So you don't really want to have to deal with scum or sediments in your digester. So to have a good screen and to have a good grit chamber is something that makes operation of a wastewater treatment plant a lot smoother. This is one side of the thing. Okay, Now the improvement of screen efficiency and reliability in combination with improvement of grip chamber efficiency and reliability has reduced considerably the problems with sediments and scum in anaerobic sewer digester. The improvement of screens are mostly due to stainless steel, because stainless steel is something fantastic. Because if you have to, before there was screens made out of mild steel, and corrosion was a significant problem. You had any screen not made out of mild steel will be corroded within 3 or 4 years. And stainless steel screens will at least last 10 to 15 years, so that's a considerable difference. And of course, we have a lot more precise production of grids. We can do a lot there, and we have a lot of improvements in automation of screens, so we can clear the screens more frequently and not have problems with clearing the screens. Okay, figure 2 to 4, we show now different screen types in domestic wastewater. 20 to 30 liter of per year in person are the screen goods which are collected with a 3 millimeter screen. Screen good quantity of a mesh size, and the screen is demonstrated in figure 5. I'm going to show you that. And the screen good is reduced to 3 to 5 liter per population equivalent as per person and year by washing and pressing. Washing and pressing is gotten popular, has been started in the 1980s more or less, and now it's standard. When I came shortly after unification to the treatment plant of Wismar, we still didn't have a washing and pressing of our screen goods, and I can tell you that's the most ugly thing you can have, because it really stinks like shit, and you have the pure shit in your screen good. And now, you know, we wash it like with pressurized water, and so all the fecal components are washed out, and then it's the sewer systems, and they will get the sand particles that have sizes major to 3 millimeters, to 3 to 12 millimeters. They will get all the stones and construction material that you will find in the sewer. That has to be cleaned by washing the sewer, not by then you just have little wagons with pressurized water, and that's how you brush with water. You brush through the sewers. This is what sewer operators have to do. They do that maybe every 2-3 years to sewer, and then they have the, let me just see the word, because I unfortunately will need this more times. Let me open my dictionary. I'll come back to I think it's a shaft. They in the shaft they will then just collect the stones and will just manually take them out of the shafts and then just transport it to the treatment plant and wash it and then give it into construction industry. As they use it as gravel then. Just a second. Okay, on the internet, let me just open my dictionary so I will find, I can give you all the words. Okay, got it here. Shaft, yeah. It's a shaft, no? It's a vertical tunnel or chamber, and about in a normal gravity sewer, you have every 80 to 100 meters. You have a shaft, and then the horizontal sewer, which has an inclination of anywhere between 0.5 to 1%. There you just have this hydraulic broom, and there they get the sediments and out, and this is where the particles, sand particles of more than 3 millimeters will collect. They will collect in the sewer system, will not get to your wastewater treatment plant. In the wastewater treatment plant, the particle size of sand is mostly between and anything that's major to 3 millimeters will anyways be eliminated by the screen. So it's below 3 millimeters and goes up to almost 10 micron or whatsoever. Now the thing is, you design all your hydraulic systems in a wastewater treatment plant. You design that any sand particle of less than 200 microns, as a 0.2 millimeters diameter, will be suspended or will be kept in suspension due to the flow velocity, or due to steering, due to the hydraulic conditions. There will anything that will sediment with sand particles finer than 200, as was the size of less than 200 microns, will give you almost like a sediment, like cement. So you can, this will not, you will not have really a chance to separate that in a grit chamber. And normally it will not make major problems in the rest of the treatment plant. So what we talk about is that we have to, that in a grit chamber, we have to eliminate sand with particle sizes of major, of less than 3 millimeters and of major of 200 micrometers. Okay. The grease and fat is not a problem. It will swim. This will sink. Now, what is with the sludge? The sludge flocks also sediment, although at a lower rate. But how do we compare that? How about now, again, first decision we have to make, filtration, sedimentation. Well, filtration with this particle size, distribution of between 200 and 3,000 micron, whenever we want to filtrate that, we need a very fine filter. And this filter is going to be clogged at a very short time. It just requires a very thin layer of retained material in order to clog the filtration. So filtration is not really an option. And due to the high difference in density, it just goes in direction to sedimentation. The only problem we have is that also sludge is going to sediment, and we don't want to have any sludge. We don't want to have any organic material in our sand, because if we have too much organic material, it cannot be used by the construction industry in making street construction of the underground for streets and walkways and ways for bicycles. This sand, so we have to separate organic particles from sand that have the same sinking velocity as sand with 200 millimeters. The question is, how big are these organic particles? So we have the sinking velocity is dp square divided delta density. So we need to look at the Stokes equation. And just give me a chance not to do anything wrong here. Just a second. I actually haven't used Stokes for a long time, but we'll find that pretty quick here. It's G times 18. That was what I didn't know. This is Stokes. So it's proportional to the d square, because this is the viscosity of the liquid, the density difference, and this is a gravity constant of 10 meters per second square. If we have the density of sand is about 2,700 kilograms per cubic meter, the density of organic particles is about, let's say 1100 kilograms per cubic meter. The density of water, we all know, it's about 1,000. So this delta density is for sand is 1,700 sand water. And the delta density for organic particles, water is about 100 kilograms per cubic meter. So we see in between here we have a factor of 17. And of course, V is, Stokes is, the result is that V is proportional to dP square, and V is also proportional to delta G. So the diameter this results in a diameter of about 4. No? So if you have an organic particle about 4 times the difference of the 4 times the size of the sand particle, it will have the same sedimentation velocity and water according to Stokes. This is what I think I might have, let me see here. Yes, I have it in here. This is also displayed in this diagram here. Here you have the different sinking velocities of over the particle size, and as a parameter in here you have the density. Here again you have the sinking velocity in meters per hour. Here you have it in centimeters per second. So this is our 200 micron sand particle, and this is meeting here the density that should be of 2.7 or somewhere. Let me make it a little bit bigger here. I don't actually know why this isn't over here, because it should be, it really should be on the outer line. So we then have, I don't know why I did this here. I think these things have been moved here because they should be a little bit more up here, because it doesn't make sense. They go, as in this has moved here. Let me see this on the original. Just give me a second here. No, my computer, sorry, I probably handed this in. This must have moved without myself realizing that. I don't know what I changed here. Of course, this intersection, this line should go up to the intersection with this density of 2.65, and then we have a sinking velocity of these particles of about 5 centimeters per second. And then the organic particles that will have the same thinking, because this then you will find out when this meets here, this is meeting this density, but this is only 1.01, so this is a smaller density difference, and then you'll find out that the particle difference is a factor of 10. So it depends a little bit on the density of the organic particle which you apply, what kind of organic particles are going to collect in your grid chamber. And I'm sorry for that, this has to be moved up to here. So this is the intersection here, this line, all these red lines should be moved up. That this point intersects with this line up here. Sorry for that mistake in this text here. And then you'll find out also that these lines will just slightly end below crossing this here, so you can read it better. I don't know why this changed, because I just put lately in there. Okay, so this is very basic, and what you can find out, and no matter what it is, like if you're talking about flocks, we learned flocks just don't have a shear strength. So organic materials that are in flocks, they are not the problem. The problem, what is going to sediment with sand particles, is organic particles that have a stronger shear strength. Do we have those particles? Yes, we do have those particles, because when I was a kid, it was a sign of wealth that you ate white bread. Bread was no corns, was very fine milled flour, and nobody wanted anymore the bread with grains in them. Okay, this has changed at least since the 1980s. It's now almost 40 years ago that this has changed. That people started. My father was always saying people. He doesn't understand that people starting to eat bird food. No. It was all the crude grains. Well, we learned it's good for our digestion, it's good for our health. And so we do this now today, that we eat a lot of grains, and if we buy a toast bread or anything like that, we like it to have the entire grains in there. And those grains easily have diameters of, or particle sizes of 1 millimeter. So they are 5 to 10 times as big. They might even have 2 millimeters. Then they are 5 to 10 times as big as the sand particles we want to separate. So they have the same sedimentation velocity as our fine sand. So in our sand, we're going to find all this bird food, which we eat in our bread. No? Well, that's why my father always mentioned that. No? Okay, now what do you do with that? We're just going to find it. And what we try to do is we try to have the sedimentation not in a an adornment or in a stationary is a nice word, not in a stationary liquid, but we try to have some turbulence in our sedimentation chamber, because that will have two consequences. One of the consequences, our sedimentation velocity, also of the sedimentation velocity of our sand, is going to be lower. But we'll have a re-immersion of organic particles, and we will apply a certain shear stress in order to break up flocks. So flocks will less sedimentate, so we're going to reduce the quantity of sludge in our sand, our sedimentated sand, just by having a little turbulence. It will not help that much with the grains. Well, what really has changed is back in the 80s, if you had a grit trap, and if you had an aerated grit trap that made all this turbulences in there, you really had about 40 to 60% of sand in the sedimentated sand. Today, you're lucky if you have 10% of the sand. It has much increased those grains which we eat in our food and which we don't digest, so they do what they're supposed to do to give us ballast.
Like insoluble fiber, dietary fiber.
Dietary fiber. At least they are not digested. They do what they're supposed to do, but they end up in our sand, in our grit trap, and our wastewater treatment plant. So we have to separate them away from our sand. Now, there is something you can do about that. So you have the sedimentation, It will nicely separate, especially for the turbulences, it will separate our unamused fats and oils. I will show you how we separate them later and how we realize that in the construction of the grit chamber. And the sand will sedimentate, also everything nice and clear. But in the sand we have huge amounts of organic material in the forms of grain corns and anything that's alike. How do we separate those? Well, we do that by altering the density of our water. How do we do that? We take our sand and we just fluidize it slightly. The sand was this organic material. What happens when you fluidize this only by 5 to 10%, then the particles start to move inside. And this suspension of the slightly fluidized solids in this water has a virtual density of almost the sand. So what happens is that we really can observe that all the organic particles with a significantly lower density will move on top of the sand. And then you can take the sand away from below with, again, you do that in a kind of cone-shaped apparatus, and then from the center, from the bottom of the cone, you take away with a screw conveyor, you eliminate the sand will nicely dewater, and the organic stuff you just flush out with water back to the sewer system. Better, you flush it in front of the screen and then you have it separated. Because if you don't do that, washing once will not help, and you have amounts of sand and amounts of grit you can find in your digester. This we actually had because there's plants. I have an observation, 3 or 4 plants close to my lab. Besides the plant in Wismar, I have an observation plant in Grevesmühlen, in Bad Doberan, and in Rostock, which is the neighboring cities of Wismar. And neither in Grevesmühlen, nor in Wismar, nor in Bad Doberan we have had any problems in our digester. No scum, no sand. But in Rostock, they have, in Grevesmühlen we have 2 digesters, 900 cubic meter. In Wismar, one was 3,500. In Bad Doberan, one was 2,500 cubic meter. And Rostock was the biggest city, 2 with 6,000 cubic meters. All of them are double cone digesters, no? Conventional European design. All pretty similar. Only in the one in Rostock, they have the effluent from the sand separation or classification system. They dump into the channel, into the primary sedimentation. And there, of course, anything, any of the solids, organic or inorganic, that are not separated by the grit, neither by the screen nor by the grit chamber, will end up in the primary sludge. And the primary sludge will go into the digester. So that's where you're going to find any sand you didn't separate neither in the screen nor in the grit chamber. And you'll find all these organic particles is fine, and you'll find all the screen grit which you didn't separate, also in the digester. So Grevesmühlen, I think, was the first digester to go in operation, then it was Rostock, then it was shortly after in Wismar, and only 10 years later was the digester in Bad Doberan. And what was the result? After 15 years of operation, we found about 800 cubic meters of sand in each of the digesters in Rostock, and 200 cubic meters of more or less pigtails, grids, and grid stuff. In the digesters of Grevesmühlen and in the digester of Wismar, we have close to nothing. We have always only a few cubic meters of very fine sand with in the size distribution well below 100, as most of it below 100 micrometer. And this sand, we have divers going in the digesters, and they take lancets, air lancet, water lancet, and they just flush it up, and then we just take it out with on the bottom in the cone we have how do you say it? A pipe, emptying pipe, and through the emptying pipe we go into one of the sludge tankers. We let it settle there, and then this is the way we take it out of the digester. That's all we have to do. We didn't have to clean them, and the cleaning of a digester is a hell of a job. No, you don't really want to do that. No. From this I learned you can do a lot of things wrong, but don't. No, with all the effluents from your sand classification or sand separation system, go before the screens again. No, and let it pass again for the screens. The water which we pump over the screen. Over the screen separation system is 17% in Wismar of our influent. That means we have about 35 to 40 cubic meters per person and year of wastewater, which we receive. 17% of that is about close to 6-7 cubic meters per person a day. And out of this 6-7 cubic meters we pump about the sand separation system, we eliminate about 3 to 5 liters of sand. So we really pump the sand good. We pump it at least not even close to 500 times through the sand separation system in order to wash it and to really get the sand. And this sand, in all of those treatment plants, when the sand is really washed and classified, it has less than 3% of organics in it. So this sand separation really works. No? It's a good system. Okay. What I want to show you, although I don't know, Sean, this red should be, I don't know, it moved, no?
Oh, did it?
Yeah, this should be up here to cross here. I don't know. It's my fault. It's on my original as well. So we might in the you have, I think, a Word vision that you can put it up here and save it again as PDF, no?
Would you put the cursor right back where it is? I'm going to take a reference photo just so I don't mess it
Yeah, it just up to the upper curve here. This should be the intersection, no?
Yeah.
Because when you look in here, this is the density of sand. And this should be sand, and then the organic will also move up to 1.1, which I did calculate here. So that should really make a difference of a factor of 4. Now, this is a Stokes equation. I had to look it up as well. I didn't know it by heart. But then you find this, this is the potential is 1, and this is 2. No? And so you have the density difference as a factor of 17 about, and then you come up with a factor of 4. No?
Just practical question. When you're doing these sand separations and you cycle it so many times, I mean, the sand will break down and form smaller and smaller particles.
No.
It doesn't?
No.
It's hard enough to...
Yeah, sand is so hard. And to grind sand, you need, not by washing, no? Okay. You really need a solid grinding system, no?
Okay.
Forget it, no? So this doesn't do any difference, no?
Not even with sand on sand?
No.
Okay.
No. Okay. Not by this pure washing, no, you can't really measure that, no? Okay. What I gave you here is also, let's first go to the text so I don't forget things here. Sand with a particle size of smaller than 200 micrometers shall cause neither abrasion nor sand sediments. That's why I told you this is why we have this criteria for separation. Sand particles have a considerably higher density than water and have a very high shear strength. In order to separate sand with the least amount of other particles and sludge, also density and particle size distribution of other particles and sludge have to be considered. No? This is what we have seen. So a filter with a mesh size of less than 200 micrometers shall retain all particles with a particle size of more than 200 micrometers. Sand is then only a small fraction of the filter residue, and the filter shall clog rather frequently. Due to a formation of a deep bed filtration due to accumulating filter residue, also sludge shall be retained in the filter bed increasingly. There's two systems you can use for filtration. There's a filtration that we showed you in the screen, where the filter media is just retaining the solids on the surface, and then you might have a filter media more like type of a sponge. This is when you take, and this is what we call a space filter, because there the filtration is taking place in the filter bed. This is basically when you want to have a fine filtration in the effluent of a wastewater treatment plant, and more frequently is used for separating ferrous hydroxide, flux, and water purification processes. No? And magnesium dioxide, mangan dioxide flux, no? And water purification. But in both cases, no, due to this high amount of sludge, which you don't want to separate, filtration doesn't make any sense. No? And due to the high difference in density, sedimentation makes sense. You get pretty nicely your grease and oil out, and you get your sand. Your sand is, however, is contaminated or is mixed with, it's not really contaminated, only mixed with organic particles with a considerable particle size of more than 1 millimeter normally, but those you can separate in what we call a high density sedimentation process, high density fluid sedimentation process. And the high density fluid you generate by fluidizing the sand just slightly, just 5 to 10%, and then the organic particles will swim up on top of the sand. No? Okay, due to a formation of a deep bed filtration, the accumulating residues, also sludge, shall be retained in the filter bed. Increasingly, filtration shall therefore not comply with the ambition to separate the sand with the least amount possible of other particles and soot sludge. No? Filtration is so no an option. Alternative options, therefore, is a sedimentation. The considerable my microphone here. Let me put it back. Okay, now put the microphone put back. Sitting on the cable here. Okay, sorry. The alternative option is sedimentation. The considerable difference of density of the sand and water, as well as the low viscosity of water independent of the shear force, favor sedimentation for the selective separation of sand out of wastewater. The problem with sedimentation, however, is that particles with a larger diameter and a lower density difference to water have the same sedimentation velocity as sand particles. We treated that here explicitly. Figure 7, which I showed you, shows the organic particles with a density of 1,050 kilograms per cubic meter with a 10-fold particle size. They may have the same sedimentation velocity as sand particles with a 10-fold smaller diameter. Organic particles with a diameter of 2 millimeters have thus the same sedimentation velocity in water as sand particles with a 200 micron with a density of 2,650 kilograms per cubic meters. If you see this here, this is what we've been looking at. If you move this up to here, this is a density of 2,650, and then this moves up to 150. It moves up to the mid-size here somewhere. No? So this and go over here. Well, yeah, somewhere here. No. 2050, whatever, no? It comes close enough. And, okay, the selective sedimentation of particles with a sedimentation velocity of 2 centimeters per second. This is 2 centimeters per second. If we go up here then, this is about where it is. It's 1/3, so it's about here. It should be really, well, it's, you know, it's 2 is, because theoretically is 5, but we apply 2 because this has something to do with the turbulences which we have in our system, so we don't have a dormant or a stationary liquid, but it moves, so we have to lower our surface loading a little bit, hydraulic surface loading, in order to still have a safe sedimentation. So if we apply sedimentation, or if we calculate the sedimentation velocity of 2 centimeters per second, rather this is really our surface loading, and the particle velocity, single velocity, has to be major to this 2 centimeters per second. Then we have a constant hydraulic surface loading of 72 meters per hour, which you can also see here. That should be, when you go over here, blah, 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 to this side. Here you have 100 meters, so 2 centimeters, a little bit below. Here's 72 meters per hour, which is our surface loading, our hydraulic surface loading, which means it's 72 cubic meters of water passing through 1 cubic meter of water per hour passing through 1 square meter of surface. Like this is hydraulic surface loading, and this is the velocity the water goes upstream if you were to have a vertical sedimentation system. And by calculation, you can prove this is also applies for a horizontal sedimentation system. So a horizontal flow velocity of 0.30 centimeters per second, or a spiral flow, reduces sedimentation of sludge by redispersing the sludge and by turbulent horizontal flow into the wastewater. Particle sedimentation velocity are reduced only moderately by the terminally horizontal flow. That was why we can't use if you move this up here, you end up probably with 5 or 7 centimeters. That we are reduced to 2 centimeters. This has something to do with the stable. Here you see the diameter of the sand corn. This is what we want to separate here, the 0.2 millimeters. And the sinking velocity ideally is by 2.3 centimeters per second. But if you have a velocity of 30 centimeters per second, you're down to 0.17, no? And you shouldn't have more than 27 centimeters per second flow, because then you get a re-immersion of your sand particles. So this is really a finely affinated system where you have to have you have to control everything a little bit to the right magnitude. If the spiral flow is induced by one-sided aeration in the turbulence, by one-sided aeration, the turbulence in the grid trap is independent from the wastewater flow rate, and not immersed fat and oil can also be separated and removed from the water by flotation and skimming. That means, well, you're going to see that. This is our today, the modern type of the long channel aerated grid chamber. And you see when you aerate it here, you get the circular flow if you do not have any vertical flow, any horizontal flow here. And if you have this means if you have no inflow into your grid chamber. If you have an inflow in your grid chamber, the water flows this direction, and due to the aeration, it's moved in a spiral form through this grid chamber. And the spiral gets longer if you have more flow, and it turns on the spot if you have no flow. But this way, if you have this circulation is that you keep the sludge in immersed, and that the sand can separate. No? Okay, let's look here. For separating the organic particles with bigger diameters and lower densities from the sand, a density separator is used. In this upstream classifier, this is what those, what I called density fluid separation systems. They're really called upstream classifier. The mixture of sand and organic particles is only slightly fluidized with process water, causing the organic particles to be washed out of the sand bed and the upstream classifier due to the lower density. Otherwise, and this is not and, this should be in. Table 2 shows the different types of unaerated grid traps. Aerated grid traps are used since, I think, since probably World War II. Before World War II, I think mostly unaerated grid traps were used. Still in countries in development, often you find unaerated grid traps and manually cleaned, so you have two channels you use alternatively. I've seen that in Ethiopia and Nicaragua, and it's less machinery and they work fine. It's only that the sand is obviously mixed with sludge and everything. No? There's not much of a separation. A more or less constant hydraulic surface loading and horizontal flow rate in the first two designs of unaerated grid traps is achieved by the intelligent hydraulic design. In the unaerated long channel design, it's still frequently, the unaerated long channel design is frequently used in small wastewater treatment plants and in developing countries. The third design shows a circular grid trap using the teacup effect. That's still used also, and you find also aerated construction of that. And figure 8 then shows the principle I just showed you in the schematically design of an aerated long chain grip trap, what is most widely used design today. For small treatment plants where the wastewater flow is pumped into the wastewater treatment plant, also hydrocyclones can be an interesting alternative. This is, as we developed a system, you can see it on the homepage of a company called Rotaria. It's like the Rotaria Club, but it's named after a bacteria which is called Rotaria, and rotaria.com, and you find it under Cyclosort there. And that system we installed, since in Mecklenburg-Pomerania we have a flat country, we don't have any, so we have to pump all our wastewater to the treatment plant. And so for small treatment plants we use those hydrocyclone systems, and then we have below the hydrocyclone we have an upstream classifier, and so we have a very compact unit for sand removal and classification. No? Okay, I showed you this diagram, I showed you this table. This is a conventional system, 2 channels. You have blades you can put in here or here, so you can use either channel. You have a drainage here, because when the channel gets out of operation, you drain the water through the sand. That kind of washes the sand a little bit. And then you wait, it's nicely and dry, and then you just remove the sand manually from the bottom of the channel, and then you can switch, then it's again ready for operation, and you can switch the blades whenever you think there's enough sand here. The design of this is a channel design. Here is a collection for the sand. You might have this also just on the bottom here. And this was lines, the inclined lines here. This is a weir, and this weir is cut in this rectangular cut, and this is where the effluent flows. And by this weir type, it is guaranteed that the more flow you have, of course, the level in the grid chamber will rise. And since this widens here, you will have, because this is a normal operation here in this conical shape here of this channel, because the more flow you have, the more surface area you need in order to keep your surface loading constant. And at the same time, you need also more volume in order to keep the resonance time or the hydraulic flow velocity constant. And this is pretty nicely equalized by this. If you really calculate theoretically, you will find out for having a constant surface loading, you will have such a shape here, as a kind of this curve here, And in order to have a constant velocity, we'll have such a shape, we would need such a shape, and this is a compromise that gets close to fulfilling both criteria. No? This is a nice hydraulic exercise and fluid dynamics for students. Another older design is this one here. I found it's just a historical thing. It's also nice hydraulic exercise for students. You come to the inflow here, the inflow comes down by a big pipe, and then you have the effluent goes first only on the outside ring, because and only if the velocity gets higher here, then more and more the inner rings are activated. And this is by activating the inner rings, you increase, of course, the surface area and the volume, and with increasing flow, then stepwise you reduce again your surface loading and your flow velocity to keep it more or less at that in the desired range. Also, kind of a nice thing if you don't have electronics to regulate things. No, and this was done before electronics was invented. Okay, this is the circular thing. I found this a lot in Russia and East German countries. They prefer the circular, and this is like a teacup effect. If you stir a teacup, you will find that the tea leaves are going to collect in the center. And this has something to do when you stir. You have centrifugal forces. The centrifugal forces will cause the water level to rise at the rim, and this will induce a current that will flow to the center. And this is how the tea leaves are moved to the center of the cup. You can try this, and also this is nice exercises for a hydraulic lecture. Okay, we don't want to bother that. It's just because it's nice.
Yeah.
It's nice, and you can calculate it, and they work. All of them have been applied, have been working. But this is now the modern design that we generally use. We have a mechanic scraper, or we suction it like your Hoover. Hoover is a word. You use your Hoover in your house. You do the same thing here. You have a pump, and you just suck away the sand, or you have in the center you have a screw conveyor. Although screw conveyor, you have to be a little bit careful that it doesn't do. It needs to be. You need to have plastic below the screw, so with the sand it doesn't abrade too fast. No? That's always a little bit nifty to get that working. And then you have your a pump where you pump water and sand away. It needs to be heavy duty pump, safe for erosion. No? This is a scraper, and here you have the Hoover system, no? Where you suck away the water with a pump here. No? Okay, this is all have to do with sand removal. So now you saw for the large particles, large particles with good shear strengths, we use a filtration system in the form of a screen. And for sand and fats and oils, we use sedimentation with a pretty high load. Sorry, what I forgot to show you is this is actually where we collect the grease. This is like a fence with wooden plates and in between holes, or you can have concrete holes, and then the grease sometimes will, due to the current here having this velocity, the grease will go through here, and this chamber will float up, and you can skim it away here with a scraper, no? And then just pump it away to the digester.
So I imagine clogging in those types of systems where you're skimming off fats and oils and waxes, they're prone to clogging, right? I mean, do you have to like heat those just?
No, because you skim off a layer and you have a bunch of water with it.
Okay, yeah, of course. Yeah.
And if you skim it over, you always make you skim it over over a rim, and then it falls down 30, 40 centimeters, and the layer of fat is not sufficiently stable to survive this fall with the water of 30 centimeters. And you have probably 50, you never have more than 50% of solid grease and fat in there. So, and because that gives you sufficiently COD concentration for the digester, you can dilute it by 1:1, it's no problem. And then it's easy to pump. No? Okay. This removal of grease from grease traps in industry, where you just have a tank where the water, for example, from milk industry passes through, and then you get a layer of 30, 40 centimeters of solid grease. Okay, when then comes the guy and he wants to take it away, then he has to destroy it first. No? Then he goes with his heavy, he has like holes with 150 centimeters diameter. It has an end of steel that's pretty heavy. So, and he has something like a crane more or less, and then he just destroys with that first the scum layer, and then he pumps it forth and back a few times and destroys the scum layer and makes it in pieces small enough so you can suck it away with all the water. And normally, if he has 30 centimeters of layer and you have a diameter of 1 meter, he normally pumps everything away because he gets paid by volume. He doesn't care, so he pumps it. He always empties the because on the bottom you have also some sludge. No, so he takes everything, and because else he wouldn't get paid for his work. No? Okay, now we have two more to go for mechanical systems, and then we'll go to the biological system. If we come back, we had corrosive material we wanted to remove. That we have done by filtration. Then we wanted sand and fats removed. That we have done by sedimentation with a pretty high surface loading. Now we have the sedimentatable organic flux we want to get out, because there's two options those flux which we can separate by mechanical sedimentation. It is just an economic consideration that we separate that. We could also send them to the aerobic tank and have it biologically degraded, or converted or co-sedimentated with a surplus sludge. But then we have all those flux in the biology, and we have to supply oxygen for degrading the biodegradable parts in this, or the biodegradable components in these flux, which would sediment. And for that, we have to supply oxygen. We have to use energy. If we instead separate it in a primary clarifier, and we have a biogas plant or a digester, then we get biogas instead of having to supply oxygen. No? And what is not biodegraded will end with a surplus sludge anyhow in the digester. So, for optimizing the energy balance and for not having all the sludge in our aerobic system, because the SRT, we have to dimension our aerobic system. So if we put more solids, if we have a higher solids inflow concentration, we have also to expand the volume of our aeration tank. It's not really very significant because, of course, we have much more activated sludge in our system than ever comes from the influent. But we also increase the COD and BOD load, and that's not insignificant, because by the reduction of the COD load in a primary sedimentation is normally, if you don't do anything, just sedimentation is around 30-35%. And in Scandinavian countries, they used this for a long time. They had only a primary sedimentation because they used a lot they added flocculants because they had so much steel and aluminum industry that they had all this waste ferrous chloride solution they couldn't use anywhere else. They put it in the treatment plants, and then you can get up to 60% of COD elimination. You get almost 80 to 95% of phosphor elimination. The only thing you don't get done is nitrogen. No? But the Scandinavian countries argued that they say, if we eliminate our phosphor, the nitrogen is not the minimal factor for eutrophication, and so we have done everything we need for protecting the Baltic Sea. It was always on international level. It was Helsinki Conference and all this kind of stuff. So that was and followed up then that the Baltic Sea was an international issue, and a lot of discussion what everybody should do in order to conserve the Baltic Sea. Well, finally now also the Scandinavian countries, so Sweden, Finland, and Denmark, also have mechanical biological systems, and also have now their nitrogen elimination with biological systems. Well, you know, in Scandinavia, however, there was also a different problem than which you have also in Iceland, which we don't have so much hassle with in Germany, is that you have freezing, you have low temperatures. No? And in Scandinavia, most of the treatment plants are housed in completely. Like in Germany, we have only very few plants which are housed in completely. We have mostly open tanks, and the wastewater is warm enough to survive our winters. This is not possible in the north of Scandinavia. Therefore, for example, also the wastewater treatment plant of Stockholm, in Bergen and Oslo, and all those things are completely housed in. And in the Oslo treatment plant, there's another problem, which is also a little bit common to Iceland. In Germany, we hardly have any rock in our soil. Well, Iceland and Norway are purely rock. And so in Norway, also they have the same problem as in Taiwan and South China. They have about 600 liters per person and day wastewater in the central wastewater treatment plant. That's due because the central wastewater treatment is some 30 kilometers away from the city of Oslo, on the other side of the fjord. And so they had to build a long sewer, and if they blow the sewer into the rock, and of course there's cracks in the rock and rainwater comes in. That has two effects. It has, first of all, the amount of wastewater is increased by a factor of 3 to 5, which is, so it comes like in China and Taiwan, it comes very dilute to the wastewater treatment plant, but in high quantity. And else it's cold. It's very cold. So in Oslo is one of the plants where I see reason. They do not have they neither have a activated sludge plant nor a trickling filter, but they have a so-called biofilter on the base of almost sand, of a little bit coarse sand with particle sizes of 2 to 3 millimeters, and so they have a very high active surface area of specific surface area per volume. They have about 3,000 square meters per cubic meter. This is due to the low temperatures, to the high volume, and to the low concentration. There's no other system that can handle that as efficiently as a biofiltration system. These systems were developed in the 80s in France, came from there, and they tried. There's one plant in Germany. It's one of the plants which I think is it's number 2 in my Luxus plants. No? Number 1 is a plant which is in Austria, but in Austria they have the problem that they have no area where they can put up because all mountains. And in the mountains is the most tourists, so that's where a lot of wastewater is generated. So what they did is they put the wastewater treatment plant into the mountain. So the wastewater enters at the one end of the mountain and comes out clean at the other end. And I just know this plant because they asked us for dimensioning the digesters. And so they said, can you dimension the digester for this plant? I said, no problem. So I draw those digesters and I send them there as, concrete structures. They said, no, we're not going to put them in concrete. We have to put them into the mountain. So I said, you know what we're talking? We're talking about 2 times 2,000 cubic meters.
Yeah.
Yes, I said, never mind, we're used to that, no? So I put the same digestive construction in the mountain if they wanted that, no? And then they said, okay, it's fine, that's what we do, and they ordered the equipment for that. So finally, I said, when I asked him when the construction was going to start, and so, you know, I said, I have to go there, I have to see that. it's 1,000 kilometers away, but I said, never mind, no, it's 2 days driving, so what's the problem? A good day driving. So when I came up from Brixen, the last 100 kilometers maybe, up to Brixen to the site, there was just one chain of trucks loaded with gravel. It was big stone gravel. No? When I came up to the side, I was asking, what was this line of trucks? I didn't even think about it. They said, oh, it's your digesters. We blasted just the first digester. No? It's, you know, if it's 2,000 cubic meters of rock, you talk about 6,000 tons. No? So you talk about 600 trucks with 10 tons of stones. No? And so you really have, I think that about 50 or 80 trucks, you're just running forth and back. You know?
That's crazy. That's one way to deal with the space limitation.
So, and all this treatment plant of Stockholm, Stavanger, Bergen, Helsinki, they're all underground plants, all blown in the rock. So it's not only Austria. In Austria, there's now 2. The neighboring plant was also blown in the rock. So there's several of those. I didn't know. I didn't even know they exist. No? But okay, that's what you learn. Volume is getting more important. So you want effective systems. By reducing the load by 30%. Makes, of course, 30% of the volume, and you will later see the hydraulic retention time in an aeration tank is about 16 hours, and in a pre-sedimentation we'll find it's 2 hours. So you can see by 2 hour retention time reducing 1/3 of the load, no? For 16 hours, 1/3 of the load is 6 hours, so a pre-sedimentation tank is only 1/3, and it improves the energy balance. So yes, it has a bunch of advantages. No? Okay, what do we want to do in a primary sedimentation tank? So we have the same system as here. We just have a different characteristics again. Now we want to settle the sludge. So we have to lower our surface load in order that smaller sludge particles, and sludge particles was a lower density surface. We're not going to aerate it because we want nothing to re-emerge. So what we did is, since we can't really calculate the sedimentation velocity of sludge, because we don't know any particle diameters, we don't know the density, and we don't know the form, because the flux are really not particles, because they're just some kind of a structure, and most of it is water. So you don't have really, this flux was a disintegrated structure, and you don't want to have turbulences in order to destroy those flux. Those flux are shear sensitive, and you want the flux to be as compact as possible, but they are just the way they are. So you have to live what you get, and so you can't calculate really a sedimentation velocity. So that's when you start to get into empiric knowledge. So what you do is you just take the water, you put it in a 1 liter. You put it in a Imhoff funnel. That's how you measure it. This one is the Imhoff funnel. The Imhoff funnel is conic glass or plastic. Plastic is better because if you work on a treatment plant, don't give the operators glass. No, they're used to steel, so if you give them glass, you get it back in pieces. No, so better you give them plastic. No, transparent plastic, and you have a funnel normally of a capacity of 1 liter. You fill up 1 liter. You set it stand for 2 hours, and you have to move it, but very gently, so it's only that flocks will not cling to the surface of the funnel, so that they'll slide down in the cone. And then after 2 hours, you look what your sludge volume is, what you get, and that's the sludge you will get in a primary sedimentation. No? That's what we define. The sludge volume which we have at the bottom, that's what we define is the volume of the settleable matter. And well, you know, from this volume you can just if there is Imhoff tanks that at the low end have a valve more or less, so you can open the valve, take out the salts, and then you can measure the salts concentration. It's usually not done because at least a pyramid of settled metal, you give milliliters per liter. No? This is how you normally qualify it. Well, you know, in a sedimentation tank, it's empiric knowledge. You can make the tank round, but mostly it's square, as it's rectangular. Width to length is about width is 1, length is 5 to 6. You will have a depth of 2 to 3 meters. If you have a rectangular tank at the inflow side, you will have a pit, a conical pit in front where you collect the primary sludge. You mostly have a scraper, might be a scraper that there's all kinds of different scraper types. I have to see if I have photos in my. Let me see. I think I have photos, no? Yeah, I have photos, so I can show you later. This is the rectangular form. This is again a scraper, a screen scraper that moves on a bridge. Here you have the inflow side. Here the effluent flow side. Here you have the spit for collecting the sludge. And normally you have a pipe then going up here with a valve and another shaft before here. This is the shaft of the inflow, and you have a baffled inflow, so it's nicely separated, so most sludge will sedimentate in front here, and only a little sludge will inflate here. Then you have a weir, you know, how do you say this? I had this, sorry. The effluent, no. Well, you have a weir with cut-ins, so you have the effluent, because the effluent weir is kind of important. I'll come back to that. And here you see in the picture, you see here the pit, you see here the baffle inflows, no? And this is a special scraper developed in Scandinavian country. It's an eccentrical move, and it moves here forth and back. And it has a steep incline in the front and a smooth incline at the back. So moving back, it will slide underneath the sludge, and moving in front, it will push the sludge forward into the pit. No? And from the pit, it's sucked with pumps, and or you have a hydraulic system, because this is deep, and you have water pressing it into a shaft on the other side, and there you can have submersible pumps that pump the sludge into the digester. No? This is normally how the systems look. This is made a photo from the pre-sedimentation tank in Staffenhagen, which is another plant. Okay, this is the efficiency. After 2 hours, you got all the settleable matter eliminated, which means you've got about 70 to 72% of the suspended solids, because suspended solids are the settleable solids, and the other ones which you can eliminate by filtration. But filtration is here very fine defined. It's by 0.45 nanometer pore size, no? which normally is difficult to measure, because this filter always clogged. No? It's a pain in the ass to measure that. And then here a BOD, and that's pretty much the same. The COD is eliminated by 30% more or less. This is an old unit. This is a COD on the base of permanganate. No? That is old, yeah. It's from my professor. I robbed it from the textbook of my professor, where I made my PhD. No? Okay, let's go through the text. It's not much, so I don't forget anything. Primary and surplus sludge are not composed of particles, but rather of flux. The flux are shear sensitive, and density difference to water is small, so the flux neither have a well-defined diameter nor a well-defined form. For soot sludge parameters, laboratory tests to measure these parameters were developed that describe the sedimentation of the different soot sludge quite well. The parameters developed are the volume of settled metal, total suspended solids, and the sludge volume and the sludge volume index. But the sludge volume index will come back at the secondary sedimentation. There it's more important. The volume of settled metal is determined in conical immofunnels. Immofunnels are made of transparent plastic or glass and have a volume calibration. When the waste is filled into the immofunnel, after 2 hours, the volume of sedimented sludge is registered. The unit for sedimental matter is milliliters per liter, and it serves estimating the sludge volume of the primary sedimentation with an average hydraulic retention time of 2 hours. Normally, if you dimension it for 2 hours, you end up in practice, because the 2 hours is a peak dry weather load, so you end up with, on average, 4 hours. No? So you're on the safe side there. Volume, settled matter, and pollution parameters in the supernatant have been measured, also for average hydraulic retention times of 0.5, 1, and 2 hours, because as you just, designing that thing for peak hydraulic load, you get pretty rather big tanks. Although tank volume, if you have space, is not very costly. So it kind of depends on the situation. If space is costly, like on a ship or something, you'll dimension it small and with 0.5 hours, because on peak load, then you'll mostly have an average of 2 hours. No? Pre-sedimentation are mostly designed rectangular with a depth of 2 to 3 meters and length to width ratio of 1 to 5 to 6. No? This is what I all told you. Then we have looked at the things here, and then we'll see. Total suspended solids are all particles that do not pass a filter with a pore size of 0.55 micrometers or 450 nanometers. So 0.545 micrometers filters clog often before a volume of 100 milliliters filtered. So for filtration, we don't even have to consider that, no? Unless the content of THS in the sample is very low, as for example in wastewater effluent. And often normal paper filters are used in order to measure TSS, which is not correct. But what are you going to do? You're going to find a solution. And if you see that your filtrate is optical clear, that's all you want. No? That's what you do.
Actually, I was about to ask, what type of membrane material do you use industrially for 0.45 micron?
Yeah.
I mean, what are your options, like nylon, Teflon, and I mean, even then they're not going to...
Oh, you can buy them. I don't know what the stuff is about. Or you can, the option is glass fiber. But that's more or less also very fine. And that works a little bit more robust than the membrane filters, which you can buy. But I don't know what material they have. But those membrane filters are the pain in the ass. No? I get so frustrated.
Yeah, I mean, I bought a couple square meters of both Teflon and nylon 0.22 micron membranes, and constantly backwashing them.
Yeah.
I mean, so...
Oh, no, this is just for analysis. You just use 100 milliliters, and you have such thing, and it's something, it's really, you have to screw them together, and you never get them really fixed. It runs all over the place of water. It's just a mess, no?
Yeah.
It's by suction, it's just a mess, no? So most of what you really do when you measure, for example, in sludge, you measure anyway TS, you do it by drying. And the filtration, the most you can do is, and you can use coffee filter or any paper filter for making activated sludge, and you get a clear effluent, so everything is nice, no? As a TSS, this is just what you can do in effluent of the treatment plant for getting those 5 milligrams. This is what you can do with those membrane filters. But for anything else, they're worthless. They're worthless, no? The filter residue is dried at 105, no, and like you do everything else. The sludge volume is measured in a 100 milliliter graduated cylinder after 30 minutes sedimentation time. This is for activated sludge, and then the sludge should be diluted if the volume surpasses 200 milliliters per liter in the sedimentation test. And then you have to multiply it by the factor what you dilute in order to get the sludge volume. And then the measured volume is multiplied by the dilution factor. The sludge volume index is a quotient of total suspended solids and sludge volume. No? Okay, and then I think we have 12 o'clock.
Oh, yeah, what we do?
And so we continue at 1 o'clock, right?
Yeah. I'm actually gonna migrate the stuff now to our next location. We are
In?
L101, so we just moved down the hall. We just moved down the hall, just to the room at the end.
Oh, okay.
Yeah.
Good. Fine. And we close it here.
Oops, there we go.
Okay. Good. Yeah. Secondary clarifier. That's a little bit longer. And then we come to the biological reactor. So I might need half an hour to terminate the mechanical stuff. No.
No worries.
In the afternoon, I have Violetta as a student. If she finds a university.
Yeah, it should be. Well, I should say it should be easy to find, but that's what I did.
Yeah,
When
yeah.
I first moved here, I did get lost trying to find things. I've got a class from 1:30 to 2:30. Then I suspect we'll have more students. Thursday was a pretty busy day for the students, so a lot of them are kind of jumping between morning lectures.
This one we have to take, or is it in every? This one is in every room. Leave it here, or
Yeah, just leave it here, that's fine.
okay. And I'll just take my stuff. And